Something amusing to start. I'm just going to read this quote. Throughout the 17th century, there was an ongoing debate in biology between the so-called vitalists on the one hand and the pre-formationists on the other, blah, blah, blah. Championed the pre-formationist viewpoint. This view argued that a complete human being was contained in either the male sperm or the female egg. You can debate whether you're a spermist or an ovist after this session. Can you see the little guy? I bet you weren't expecting to see a picture of that in this talk. The pre-formationists argued that there was a simple and direct mapping between the seed of the organism and its end state, simultaneous growth of all the body parts. Indeed, pre-formationists of a religious conviction argued that God on the sixth day placed about 200,000 million fully formed human miniatures recursively into the ovaries of Eve or the sperm of Adam. All right. Okay. What idea in modern ML does this remind you of?
The culling.
Yeah.
That sounds a lot like that.
What's the precise?
Lottery
Lottery ticket. Well done. Okay. I'm kind of not a fan of the lottery ticket hypothesis, but anyway, the point of showing this is like these are not new debates, people, right? Like the nature of how structure emerges in systems goes back to the very beginning of people trying to study systems like this. So it's worth maybe being aware that there are very interesting pictures and also ideas out there in other disciplines. It's also worth noting that, so the pre-formationist idea, I got this is from a textbook I read on cognitive neuroscience. It goes on to sort of explain how this debate, of course, came to look silly once you got microscopes and couldn't find the little people inside the sperm anymore. But somehow the idea stuck around, right? For a very long time, people sort of had the idea that DNA coded directly for parts of the body, right? And they'd look at the DNA and there'd be like the instructions for the fingers and the instructions for the legs. And to some extent that's true, but it's much more complicated than that, as we now know. And it's not like you just read the DNA and then written in there is like basically a little man, right? Or a little woman. That isn't how DNA works. That isn't how development works. And well, this is a textbook on developmental neuroscience, so of course they're committed to a certain way of thinking about how growth happens, which is of course correct. Okay, this is meant to be an open problem session, but I found myself when trying to explain why I think particular problems are important, it's sort of impossible not to explain the method in the madness, so I'm going to explain a little bit of what we're up to and why. Through various stages of the sort of DevInterp program that we're trying to execute. The early stages are the things about which we're not surprisingly more confident, and then it gets a little more ambitious later on. Level 0 is what we've been doing, right? Using things like the estimated local learning coefficient, lambda hat, the singular fluctuation, to detect and have some understanding of what happens in phase transitions. I'll go through the details in separate slides, but just as an overview. Level 1 is something we haven't really talked about in public, but which is things that we're trying to do right now, which is given that you have found transitions, try and reason about how they're related. The ideas there come from catastrophe theory. SLT-4 back in the primer sort of sketched how we were thinking about that. We don't understand this yet. These are ideas. They're sort of maybe will pan out in experiments shortly. Then it starts to get actually hard, right? So this is kind of actually maybe novel from the point of view of ML, and certainly the role of singular learning theory in these quantities is novel, but there's precedence for many of these ideas, either in statistical physics, solid state physics, or in this case in developmental biology. You can sort of make a plausibility argument for many of these ideas based on other parts of science. But although phase transitions and catastrophe theory and many of these ideas have been connected to development before, nobody's really made much progress in finding something really like algorithms in some strong sense underneath all that. And so that's where we start to really be doing new things. Up until that point, it's, I think, the novelty is sort of mostly in the fact that it's being run on neural networks and making use of SLT. And then we get into the stuff that has to do with logic, which I'll sketch briefly. Okay, this I'll be fairly brief because we've talked about it in the past. You can think about using things like lambda hat and various other derivatives as being consistent with a general idea of using generalized susceptibilities in thermodynamics to detect phase transitions by looking for divergences. Exactly which generalized susceptibilities are the right ones to use? Well, we sort of have generic ones, which are lambda hat, nu hat. I thought I had, I think I'll, okay, there's a next slide about doing better than that. So maybe I'll, this is a point that's come up, actually Colleen was asking about it yesterday, right? So even though we're talking about phase transitions, and as I'll argue in a moment, the phase transitions that happen in the Bayesian posterior conceivably are related to genuine second-order phase transitions, to which such things can reasonably be associated. It isn't that the whole system is necessarily involved in those phase transitions. So you should conceptualize that perhaps as being like some subsystem undergoes a phase transition. And if the subsystem is small relative to the large one, then, well, whatever quantity which is in principle diverging, in reality no quantity really diverges in a finite system, its divergence sort of is constrained by the scale of the subsystem, right? So if it's diverging, but it meets the size of the small system, and that is small relative to the large system, that divergence could be like a barely perceptible bump in the overall metric if it's evaluated on the whole system. So this is one of the key obstacles, I think, to making use of the idea of phase transitions and detecting changes in structure in large neural networks. Yeah. Not all of them are like that, though, right? So if you're familiar with the in-context learning example, this paper from Anthropic that I've mentioned already in my earlier talk, in which in-context learning emerges, that's sort of a global thing that changes the way the entire network computes, or at least that's the way it's interpreted, and I think that's sort of a consistent, reasonable story. I buy it. One of the reasons you might believe that it's a global thing is that it appears to shift the scaling exponent. I'll show you this graphic later. We haven't investigated this independently, so I'm just sort of believing this part of their post. But even, okay, just supposing you buy that that is correct, that the scaling exponent shifts at this point, that's clearly a global thing, right? So this is an example of a phase transition that does involve the whole system. Okay, so there will be transitions perhaps of various scales of subsystems, and maybe you can only detect ones above a certain relative size, and we just sort of hope those are the most important. Yeah, all right, so yeah, that's just a sort of argument for if you're going to detect phase transitions under the hypothesis that the ones you care about over training are related to Bayesian transitions, then quantities derived from SLT are good candidates. And yeah, as I've mentioned, these are what we have right now. Okay, so starting with open problems. So far we've been focused on these and a few other things. I guess these will come up briefly in Jesse's talk. We're sort of actively developing the use of PCA trajectories in studying phase transitions. This was also in this Anthropic post on induction heads, but it's a common technique in chemistry and also in biology where, well, I can say quite a bit about it, but it's like sort of, maybe it's tricky because even random walks, when you apply PCA to the trajectories, gives you things that look kind of interesting, these Lissajous curves. And so when you're looking at PCA trajectories to reason about transitions, you're looking for discontinuities or kinks, and this can be a little delicate. So covariance matrices are a technique we haven't really gotten working yet. That's something that's also coming from developmental biology. But what I want to list under open problems are not those things exactly, but something to do with this earlier problem of phase transitions being too small, which is what I'm going to refer to as localizing the invariance. So I'll come back to this, I think, on a specific slide later. But there are various things you can do to the model truth prior triplet, or quadruplet if you include the parameter space. And those modifications, or morphisms, change these invariants, and you can think about making use of a richer sort of supply of these invariants just based on this. If this is all we have for now and we know how to get that working, we can get more mileage out of those. Yeah, I do think people should spend some time trying to come up with new ideas for quantities that are based in SLT that might be good generalized susceptibilities. I don't think anybody's really tried very hard to do that. But this is the paper to go and look at, a very beautiful paper. It sort of is really the place where SLT is presented most in a sort of statistical physics language. And we have at least some confidence in our posterior sampling now and some of these ideas, cooking up some ideas and trying them out, detecting phase transitions in the systems where we know that they exist, right? So there's lots of scope for coming up with new detectors at this point. Yeah, this is a point to do with better samplers. Any progress we make on quality of approximate posterior sampling, the kind of stuff that Zach's been talking about in the breakout sessions, obviously yields dividends in finding transitions, especially if they're relatively small. Small meaning that the subsystem undergoing the transition is small relative to the whole system. System meaning neural network, so the ratio of the number of parameters, I guess. The better we can get at posterior sampling, the more resolution we'll have on detecting transitions in smaller systems. Yeah, one thing I want to emphasize is it's easy to sort of get over-ambitious and overestimate where we are, right? So our approximate posterior sampling and our estimates of the local learning coefficient are extremely preliminary, right? Like in terms of astronomy, if this science were astronomy, we're learning to grind glass. We're not out there building space telescopes, right? So one should be rather humble and systematic and in a stepwise fashion trying to improve these tools generation after generation. And I think that's the right approach rather than sort of just, well, now lambda hat works. Now let's go and reach straight for the stars. It's fine to measure that, to try and do ambitious things, but we're going to make more progress on these basics, and I think that's important. Maybe I'll pause at the end of each one of these particular slides for any questions.
What is noisier but more sensitive? Higher order derivatives will be noisier but more sensitive.
Yeah, okay, thanks. So when you're looking for phase transitions, higher order derivatives will tend to be a stronger indicator of the transition, right? Of the free energy, yeah. So, if you have like in a second order phase transition, the first derivative will be continuous, but the second derivative will have a jump. So that jump is going to be much more visible than something in the lower derivatives. But the more derivatives you take, the more the sort of quality of the approximate sampler is going to matter. So, yeah.
Is there a clear thing I should have in my head when I'm thinking of, I think you said yesterday that like the straightforward picture of phase transitions only talks about first order phase transitions.
Correct, yeah.
So I shouldn't have a picture in my head of what you mean by the second order phase transitions.
Yeah, that's an error in my talk and its order, so that'll come up in a moment. Yeah. In fact, right now. Okay, so it helps to explain, I've mentioned to a few people how I think about the relation between the first order phase transitions, which we've spoken about several times, and second order phase transitions, which are what you want to be talking about if you're talking about emergent structure or the kind of things I was just speaking about. This is a conjectural story. We're in the process of trying to establish it in some examples in TMS, theoretically, and also experimentally. So this could be wrong, but this is how I'm thinking about it. Maybe it's helpful to see the kind of the argument. So dynamical transitions, just to repeat myself from yesterday, this is just what we observe over SGD training, right? The trajectories pass nearby multiple critical points. You see plateaus. This is the ground truth, perhaps, that we care about for now in gradient-based training. But it's also the kind of transition which is sort of mathematically and sort of otherwise maybe the least satisfactory and difficult to reason about. So what we sketched in the TMS lectures, Edmund and I, was a preliminary relation between such things and Bayesian transitions, which are first order phase transitions in the posterior as the number of samples n changes. Those are easy to reason about using the free energy formula, but then it's not. I mean, the relation between these is sort of speculative. Maybe it looks plausible in this one small system. What could possibly be like a principled reason to believe in this connection? Well, there's a third ingredient, which at least in the case of TMS, in some very specific critical points, can be shown to be involved, which is catastrophes. And this is there's very clear links between these two stories, which are sort of what catastrophe theory is about. So catastrophes, okay, so a second order phase transition from the point of view of varying a control parameter and watching something happen to a singularity has to do with a change in configuration of critical points. Right? So a first order phase transition is associated with a change in the configuration of critical values, where I'm drawing with my hands 2 points in a free energy curve, one being lower than the other. So this is the preferred phase. Those are the critical values, the heights of my hands. As the critical values shift with the change in some parameter, temperature or pressure in thermodynamics and N for us, the critical values, the configuration, it goes from being 2 distinct critical values to 1 critical value. That's the change in configuration of the set. And that's a first order transition. Second order transition in this sort of geometric sense is a change in the configuration of the critical points. So 2 critical points merging or splitting is the typical picture. So mathematically speaking, catastrophe theory is a study of moving in the unfolding or sort of moduli space or parameter space of these singularities. It's stated in terms of control variables, which are the things which you vary in order to do the thing I was doing with my hands, right? So the control variable is the dial which is being turned and which induces the critical values to change or the critical points to change. And the x are the so-called state variables, which are the variables of which the potential is a function. Now, the connection that I'm sort of arguing for between these 3 works as follows. In some neighborhood of the critical point which controls a phase in the sense of Bayesian statistics, you can ask for a division of the parameters into control and state variables in such a way that the Bayesian transition, which involves a shift in the posterior as a probability distribution over W's, that's a discrete jump, if you like, that happens as n changes. But you could ask to have lying behind that discrete jump some kind of process where something localized near one critical point, as a control parameter varies, becomes localized around another one, and sort of have associated to the Bayesian transition a motion through the control space of some catastrophe. This actually is the case for the foregone to five-gone transition in TMS. That's like one example. So this is not very well supported, I would say, at least in the examples. But this is a relation in principle between a second-order transition and a first-order transition. And if there is to be any connection between, the mystery, I would say, at least for me, is why you would expect at all this kind of transition, phase change, to be related to critical phenomena. It's not obvious. But once you understand the bridge to catastrophe theory, there are genuine second-order phase transitions here. So this connection is very solid. This is classical. This is not me inventing this. So this link here is very solid. This link here is the thing that we were sort of arguing for as thinking about the obstruction to there being a dynamical transition being something to do with the free energy. Okay, so this we have some evidence for in TMS, and hopefully we'll accumulate more evidence, we'll see. But to the extent that transitions that occur over training are consistent with the free energy formula, which is a general intuition that people have expressed independent of SLT, right? The idea that, for example, in saddle-to-saddle dynamics, that drops in the loss are associated to increases in some kind of measure of model complexity. This is kind of like a broadly accepted, believed idea. So these two links here we've sort of seen some argument for. The link here is something that hasn't been developed. Yeah.
So we're meant to think of a drop in the loss in the dynamical transition as simultaneously a first-order transition in the Bayesian perspective and also a second-order transition from a catastrophe perspective. It's not like we can look at different transitions in the dynamical setup and call some of these should be thought of as Bayesian.
No, both.
Some of them should be thought of as catastrophes.
That's right.
They're all both.
That's how I'm thinking about it, yeah. And in particular, I wouldn't say that, it's not that so when I say dynamical transition, actually what I mean internally is a trajectory that passes from one critical point to another in such a way that it passes through a loss landscape configuration that can be split into control and state variables in such a way that this applies. Because otherwise it's very hard to understand why such a thing should be. If you say that structure emerges in a dynamical transition and you want to sort of have some physicsy way of talking about that, I don't actually understand why that should be valid unless this is true. So maybe you should think about this as actually being a constraint on the set of dynamical transitions that you think you can treat mathematically. And then it would be a conjecture that many of the transitions that we observe over neural network training, in fact, are controlled by catastrophes. And you can blame our friend Renee Thom, whose name I wrote up there, for perhaps this idea. Okay, so that's how I'm thinking about the relation between these three sets of things. So once you've seen that idea, you can sort of understand what we're getting at in trying to connect different transitions. And the idea is the following. It's that if you see a structure psi prime, which emerges in some phase transition in neural network training, then you could think that it depends on some earlier structure if the following technical thing is satisfied. The idea is just the sort of obvious fact that over the course of development, say in biology, structures don't all form at the same time. They form in some order, and earlier structures are relatively fixed background environment for the later structures that form. And, well, you will find described in the biological literature this fact in terms of earlier developments determining the governing potential for the development of the later structure, which in the language we're discussing here is the setting of control parameters. So translating that into mathematical language, it says that if the transition responsible for psi, so that's the, which order around is it? Psi is the first one, yeah. So If the first one involves a division of the variables locally, in the sense I was describing on the previous slide, state variables, control, and other, these are just parts of the system that aren't involved in the transition, either in constraining it or as the emerging structure, that's the X variables. That's the initial structure that forms. Now that's like fixed background for the new structure that's forming, psi prime. And you would say that psi influences psi prime if the control variables for the second transition have some overlap with the state variables for the first. That, of course, then raises the question of, well, how do you tell what are state and control variables? Is there some way of inferring that from data? Those are very good questions, which Edmund will answer in 2 months. But those are in principle resolvable questions. We don't know how to resolve them, but those are reasonable things to study. Okay, so that's how I'm thinking about going from this picture of detecting phase transitions to just as some isolated things, trying to see some connection between them. Yeah. Okay, I think I want to move through this to open problems. This is the part where it gets more speculative. If you want to go from detecting relations between transitions to trying to back out something that's arguably an algorithm, you need to know more than just that two structures are connected, that psi influences psi prime. You actually have to have some understanding of how that influence occurs. The way that fits into the story, as far as I can see, is that the way in which it influences the later structure is to do with geometric structure that's changing at the phase transition. And this is where you want to have better tools for probing the nature of the geometric change at the transition. That kind of inference is really novel. So as I was saying at the beginning, what I was calling level 0 and level 1 is in some sense a riff on things that are done in other parts of science. This I do not believe really has much of a precedent, so maybe that means it's not possible. But it's also the case that nobody has really tried with the tools that we can see in front of us, right? Once you have SLT and you have all these other ingredients, you actually see obvious things to do that I don't believe anybody has tried. So there's the technical terms here are the continuous Lyapunov equation, and there's some work by Oku and Aihara which we're actively developing right now. And there's some principled relations to geometry. So this is how again, this isn't working, but this is how we're thinking about trying to detect the higher order changes the changes in geometry that happen at phase transitions, and then try and relate that to the relation between the emergent structures.
What do you mean by Lyapunov equation? Which of them?
Sorry?
What exactly do you mean by Lyapunov equation? You mean for infinitesimal displacements of a solution of an ODE? That one?
Yeah, that's right.
Perturbations.
Yeah.
Because he has many equations.
Yeah, well, that's true.
Can you say something about the kinds of higher order structure you're interested in? Like the types of thing we might be interested in?
I mean, the examples that are sort of obviously going to give rise to something that you might be able to detect here are things like when two circuits are actually connected together. So actually I'm not committed to circuits as a model of computation, but to the extent that circuits are the right way of thinking about it, if you have some parts of a circuit influencing other parts of a circuit, then you can sort of see some sense in which there's degeneracy arising from that, and that should be something that would be visible to these kinds of techniques. So when I say, maybe I should say, so higher order here is just referring to the fact that usually when you're doing the continuous Lyapunov equation, you're basically expanding something only to second order, right? But in principle, there's higher order terms that you can put into that equation, which are related to higher order jets.
So you are talking about the difference between linear stability and...
That's right. That's right, yeah. So like in catastrophe theory or these subjects, Of course, they do stability analysis, but once you go past second order, especially when catastrophes are involved, you have to start doing geometry then, which is where, of course, all these books stop. But it's not like the theory stops there. It's just that the books stop there.
Well, there's a reason people read, it becomes very hard.
Yeah, that's right. Okay. So if you want to think about those things as algorithms, then you have to come up with some notion of algorithm. So supposing that succeeds, so you know how to connect different transitions, you know how the emergent structures that arose in those transitions are connected together, you have something, you have some notion of how the thing is computing, but it isn't that you necessarily just look at that information, which, I mean, what is that? That's a bunch of critical points and some kind of higher order geometric information that tells you how some transitions are related to another. It's not on its face an algorithmic object. So it's not that you naturally look at that and know or have some correspondence to some form of computation that's familiar. So my idea at this point is to make use of existing logic. All right. So this is a sort of explainer for why this story with linear logic and SLT has sort of been going on and how it fits into the DevInterp story. So this we've talked about plenty, right? So neural networks, they're learning machines, modulo like Bayes versus SGD and all that. You can formulate this theory of neural network and the learning neural networks and the learning process in terms of SLT. What does that mean? Well, it means that you're talking about neural networks in a language that is talking about the Bayesian posterior, phase transitions, and the rest. So it's the language of statistical learning theory. It isn't obvious that you can talk about the ingredients of classical computer science in the same language. Right? This seems quite far away. Yeah.
Go on.
No?
Complete your story.
Well, the story will take 5 minutes. You're going to hold your hand up for 5 minutes?
Continue.
Okay, I'll continue. So it's not obvious how to put this into this framework. There are plenty of ways in which you can take classical models of computation, say Turing machines, and embed them into something continuous. But the problem is that just embedding Turing machines into a continuous space doesn't necessarily mean that what's happening in between those discrete points, which represent your classical model of computation, has any intrinsic meaning or interest. Right? So it's actually relatively difficult to come up with an embedding of proofs or programs into a learning theoretic setting in such a way that the stuff you do here actually has content that reflects computation. And that has been done to some extent in, say, Tom Waring's thesis and some of the other work that's in the same line of development. I would say this is like a beachhead in some strange territory, and well, you don't camp out and live on the beachhead. So this stuff is quite ad hoc in some respects. But what I want people to take away from this at this moment when you look at it is not that this is meant to be the thing. This is meant to show you that it's possible in some principled way that's quite serious to take classical computer science and put it into the framework of SLT in such a way that things like phase transitions actually are genuinely meaningful and say something about the original theoretical computer science systems, say Turing machines. So if we can succeed in understanding that bridge, maybe not these particular ways of building it, but this shows you that it's possible. If you can build bridges between these two objects, then you can start to look at the structure of programs and ask what the corresponding structures and effects are here. Yeah.
So there may be models of computation. Turing machines is one, so the whole story lambda calculus is another. However, why not use something that is closer to neural networks, like circuits of various forms?
Circuits.
I don't mean like the OLA, really totally ill-defined circuits, but Boolean circuits and other ilk.
Like with like probabilistic circuits, perhaps, in order to put them.
I don't know exactly what, but it's something like that.
Yeah.
Perhaps.
Yeah, I think that makes sense. The problem is, I guess Alexander and I have gone around about this a few times. The problem is universality. So it's not that interesting to have a fixed program which you then sort of make probabilistic in some way and stick into the framework of SLT. Because you actually want different regions of the configuration space to correspond to different algorithms.
Yeah, but I mean, do we think LLMs are universal? Like what?
Yes.
Basically, just commenting on that. I'm not very involved with the details of this discussion, but just from a high level, it seems to me that the assumption that you make of the kind of algorithm you expect to find in there, if it's like a Turing machine or if it's some circuit function, Boolean, whatever thing, it doesn't seem to me like the actual relationships you get out from that Schindler's landscape would depend all that much on the initial formalism you choose anyway.
Correct, yes.
And then further, like Alexander was saying, I mean, it's not like we need a giant universality class of all the things we can stick in there. Neural networks are like pretty general-ish, but with finite depth, there's only so much a certain region, circuit, call it what have you, can express. So if you just stick that in there and see what the loss landscape says, what kind of phase transitions that should result in, but it doesn't seem to me like this is actually a problem, basically.
Mm-hmm. Yeah, I would agree with that. I would say that sort of broadly speaking, I would like people to start with models of computation where we know what we're talking about. We know what structure means, we know what composition means, we know what like loops mean, we know what variables mean, and put them in this framework and then see what kind of geometry comes out. Like basically nobody's even started doing that, right? We'll learn a lot no matter which model of computation we use. But there's like the reason to do Turing machines and UTMs and all of that is partly the same reason to define UTMs in the first place, right? Like with quite a lot of effort, it is now like a theorem that you can take universal things and do this to it. And that gives you some confidence that this is not like just some ad hoc silly thing you're doing, but like actually something that's like genuinely supported by some well thought through mathematics. Whether that's the actual thing you want to do is a different story. Yeah.
Well, maybe we should
move on. Yeah.
I mean, I have thoughts, but...
Okay. Yeah, I think we could talk for quite a while about this, but I want to move on to actual open problems. Okay, so that's some setting, some explanation for what we're up to and sort of what the long-term idea is for how to actually figure out what we're talking about when we talk about algorithms that emerge from this story with phase transitions and so on, or at least one source of ideas. Okay, now I've got a bunch of open problems across many different topics, much of which have nothing to do with the story that I just told you. And I'm going to go through these fairly rapidly, okay? Because we've used half an hour, is that right? No, we've used an hour. When did we start? Yes. Which one was it? Quarter past?
You still 20 minutes.
20 minutes, okay. All right, singular fluctuation. Yeah, so we have Oyagi here. She's an expert on how to think about this. We don't actually have upper bounds on the singular fluctuation. If you don't know what the singular fluctuation is or why you care about it, there's a talk on the MetaUni SLT seminar where I go through, Mickey put up the definition, which is kind of fearsome, some ratio of some integrals. There's other ways of thinking about it that make you sort of understand what this is talking about. We have some reason to believe this is actually useful for talking about type B transitions, perhaps. So this will start coming up more in the conversations we have about applications of SLT. But at the moment, we're quite ignorant about this. It's not upper bounded by D on 2 or anything like that. And I at least don't understand any upper bounds.
Can you say a few words about why we care about singular fluctuation?
Yeah, I guess I already did to the extent I'm going to, which is that it seems to be useful for talking about these type B transitions. So maybe it's, well, we started off thinking it might be useful for detecting transitions, then we went through a period of thinking that wasn't going to be the case, and maybe now we've gone back to thinking it will be. So I would say our update now is for caring about the singular fluctuations. So there are theoretical questions there that deserve further study. But even, I mean, that's sort of maybe too focused on applications. This is a core ingredient in SLT that hasn't been studied and should be studied. Also the geometric significance, I know Simon's thought about that a bit. Maybe he could say something about it in a session tomorrow. Yeah, this actually I put on the slide before Professor Ayagi's talk this morning. Multiplicities apparently are very interesting for deep linear networks. I don't know how to actually estimate them. That would be interesting to be able to do. Lower order terms. A lot of these actually came up in the open problem session back in Berkeley, so maybe I'm not going to read all of them. Yeah.
Well, I want to say that I think that the answer is no.
So no?
Or is it reasonable to assume relative finite variance for NNNs? Because it implies essential uniqueness, and I would expect just in general the world doesn't work that way.
Yeah.
I mean, yeah, there's ways you can modify this. Yeah.
Yeah, I think that's perhaps a valid answer. Okay, so then the question would say, so we've been assuming it sort of for the moment in applying SLT to neural networks just because, well, you have to do one thing at a time. But in which directions does one have to push the fundamental theory in order to overcome this when it fails? Maybe that's the question. Yeah, this I'm very interested in. Maybe this is the wrong audience for it, but there's sort of a hard step in applying SLT or using algebraic geometry in SLT, which is the transition from the analytic KL divergence to an algebraic function. I'm just writing it as HW, to which you can do blow-ups and so on. Right, Professor Aoyagi is one of the great experts in the tricks that are involved in doing that translation. There's a suggestion for how to do that in general in remark 7.6 in the Grey Book. I can't understand that remark in the sense that I don't know how to prove the statement that's given there. I think it's a recipe for how you might do it in an example. Somebody can correct me if they can understand it. But the general question here is, in some sense, applying algebraic geometry to specific systems in SLT is sort of bottlenecked on this step here, which at least I don't understand in great generality. So that's an interesting fundamental problem maybe to work on. Yeah.
Just explain more about what the statement is.
What's H and W?
What's H? Yeah.
It's a polynomial.
So you want to bound it from below and above up to a constant.
That's right. Yeah.
Yeah, I see. Okay.
Yeah. That's not, well, that's related to sort of deep problems in functional analysis to be able to do that, so it's not trivial.
Are you looking for some sort of modulus of continuity or something of that sort?
You're thinking of a different kind of bound. I don't think it's...
Like a Breslau space or something like that.
Don't quite follow you, but I'm not sure what the answer to that is. But it's... if you look at remark 7.6, basically you can Taylor series expand the log density ratio, and then you look at the coefficients, and this is the and then those coefficients are polynomials in W, and you can stick those in an ideal to which you apply the Hilbert basis theorem. And the idea is that sort of if you sum all those up, you should get, you sum up the generators, you should get an algebraic function. But actually, I'm not sure that really works.
What does that mean?
Well, I don't know. I can't spend too long on each slide, so I don't know how to format this discussion, but happy to have someone. This has come up. This has come up earlier. We believe in phase transitions in the Bayesian posterior now, but the theory is lagging behind. There is no published rigorous treatment of this story. That depends on getting some foundational things in order. When I say open problems here, I mean like these are things I care about. Maybe we're working on them, maybe we're not. Right now, nobody's working on this. If somebody wants to tackle this, that would be terrific. So just to briefly say what the issue here is, so the way that the discussion of the free energy formula as an integral that splits into pieces is treated, and the way we've discussed it in the slides and in the paper, is just to apply the free energy formula to these submodels. There's some conditions like relative finite variance and also semi-analyticity of W alpha that come into that, but in particular, the minimizer of the average log likelihood L has to be in the interior. A minimizer has to be in the interior of W alpha, and that's not always sort of a reasonable assumption. That's related to metastable phases that I'll get to in a moment. So there's boundary issues. You can deal with those, but it's sort of artificial a little bit. Anyway, so maybe the details aren't so important, but I just want to flag that there's sort of like unresolved, somewhat technical issues to be dealt with.
Maybe the coarse graining shouldn't be chosen in such a way to have critical points on the boundary.
Yeah, well, it would be nice if you could make that choice. Obviously, what I'm saying is...
If you have isolated singularities, then you can. Allow for non-isolated, which means non-compact.
Yeah, well, unfortunately, there are such things as what they call semi-strict or strict saddles, right? Where you have a critical point, it's degenerate in some direction in the Hessian, but it's got all positive or zero eigenvalues, but a decreasing direction.
Yeah, but I mean, you can still choose W alpha. It's an isolated critical point, right?
It's isolated, yeah.
So you can choose W alpha.
Yeah.
Set with non-intuitive, you can choose it so that that's...
We'll talk about it later, yeah. I'm glad you think the problem is resolved. Yeah, so it's not always going to be the case when you talk about phases in the SLT context that, I mean, they're not all going to be local minima or things that are like local minima. And we want to actually, I mean, what you observe, say in the case of saddle-to-saddle dynamics, and this is also true in TMS in some situations, is that you get things that effectively behave as though they're sort of like stable equilibria, in the sense that the trajectory stays nearby some critical point or some critical submanifold for quite a while. That's either just because of the temperature or the noise or some separation of time scales. But when you actually, so that's fine from an experimental point of view. It's a phase and it behaves like a phase, at least at the values of n for which it's supposed to be considered. But when you go to actually theoretically treat these things, you have to deal with issues that to do with what's on the previous slide. Type B transitions, I reminded you what those were yesterday. They'll come up in Jesse's talk. We should be looking for more of these. Maybe that's a topic which can naturally come up in the discussion after the talk on in-context learning. This has come up, Jake was asking about this. I don't know the answer to this. I think Nina and Dimitri probably have opinions about what the relationship between these memorization/generalization transitions are in SLT. Maybe it is that they aren't transitions in the sense of SLT, if I remember Dimitri's comment the other day. But in general, there's some relation between type B transitions and the difference between memorizing and generalizing solutions, I think. And that would be interesting to try and explore in toy models. And this is a place to start, very related to the setting in which the TMS paper is written. There's a follow-up paper which in principle treats some of these issues. There's a lot more to be done with TMS. We're going to write one more paper on it, but we're not going to touch probably any of these issues. Doing it in higher dimensions, looking at different kinds of transitions beyond the ones that we've studied so far, using it as a test bed for transitions that are less visible in the loss, considering lower sparsity. That's not something you probably want to do theoretically, but experimentally, now we understand what's happening with the high sparsity limit. I think there's good reason to go to the lower sparsity setting, also to consider varying importance factors. This I'm pretty keen on, right? So, phase transitions in Bayesian statistics are not a thing currently, right? Because you need SLT to believe in them or understand what they are. But Markov chain Monte Carlo samplers, or just posterior sampling in general, therefore doesn't really have any good test cases for, well, am I sampling properly around where transitions happen? So once we've isolated such examples, they become maybe good test cases for, even just classical samplers, but also using it as an investigative tool for alternative posterior samplers. This I think has come up several times. Maybe I have some opinions, I'll just flag. I think we should figure out the right questions before we try and figure out the answers. So when you're trying to come up with better posterior samplers, what do you mean by better? Right? Are you trying to get more accurate RLCT estimates? Is that actually what we need? If we're comparing RLCTs of models with 100 million parameters, is it a big deal if it's off by 100? Well, maybe not. So is that actually what we want out of these samplers? Yeah.
Just making a comment that for some of the stuff we're thinking about, that actually would be really useful.
More accurate or?
Yes.
More accurate, okay. Yeah, well, that's good to know. It's actually a little surprising that, for example, in the in-context learning models that we've been training, they're quite large models, but in the end, like the RLCT differences are like relatively tiny. So even though the systems are quite big, you end up caring about accuracy more than you think you might. But still, it's a little, so I think it's great to want to get more accurate estimators of the local learning coefficient, but it's also like the obvious thing to test to try and see if you're doing a good job with your samplers. So I want to sound a note of caution to not just only chase this as the only thing that you're trying to do when you're innovating on the front of better posterior sampling. I don't actually have a good answer to what the thing you're aiming at is, but I would suggest that maybe we put a lot of thought into that, and then then this discussion that we've been having this week about better posterior sampling, maybe the next time we have a meeting, it's not is this idea for sampling, does it sound better than this other idea? But we actually have a systematic set of metrics by which we say, well, it's better at this and this and this, and we can actually have some kind of coherent discussion that's more directed. So that's kind of part of advancing the field, the science of approximate posterior sampling and lambda hat estimation. I don't know if you guys have comments on that. This is what I was mentioning before. I think this is, I've seen several people comment on some variants of this. It's a natural thing to try and do. So I guess I'm just encouraging that. You can ask the question of, well, if lambda hat is a measure of model complexity, and you kind of notice it increasing when a model seems to be memorizing something, you can ask the question, well, where is that going, that information? For some meaning of where. And so this is the obvious thing to try and do, which is to fix the model parameters in some direction, and then sample in the other directions and see how that affects the lambda hat estimate. As far as I know, this hasn't been systematically explored yet. Restricting to particular subsets of the data is also a sensible thing to do. But just in general, there's a direction of innovation in SLT which looks like vary the quadruplet, right? And see what happens to the various ingredients. And that's, now that Lambda hat is working, one should quite systematically investigate this. Yes.
So there are lots of classical notions of model complexity in classical statistical learning. I don't know anything about it, but something dimension, something else dimension.
Yeah.
Is that an approach to doing this kind of localization parameter space, or?
I don't understand the question. What's VC dimension or whatever got to do with?
Maybe, well, you want to find observables that sort of tell you what you're restricting to, like how do you choose these restrictions?
Oh, sorry, then I wasn't clear.
I mean, maybe I'm
Yeah, okay. So you start with some quadruplet. This is the model that you could estimate the local learning coefficient for, but you could also take some submodel and do the local learning coefficient for that.
I think Alex's question is like, how do you decide what subset of the space to search for? And I think, like, I don't know, my current take is you could just use, well, you could use some heuristics, like, you know, where are the activations, you know, most sensitive to the thing you're measuring, or like where the gradient on is high or something. But I don't know if you have like more principle or anything about that. Or you also can just look at like parts of the model, like there is intrinsic modularity in the structure.
Yeah.
Yeah.
Yeah, those are basically the only ideas I have. Yeah.
Okay. Thanks.
This goes back a little bit to Colleen's question about what happens when you sort of think about a hierarchy of models with more and more parameters, right? So these questions of how do these things vary in families of models is sort of part of the story of, well, there's currently nothing really like volume if you talk about the sort of intrinsic size of the system, unless you consider families of models. And so it's kind of interesting to consider how Lambda behaves with respect to such changes. Yeah, this I really want to flag as something that, oh yeah, that's for you. Yeah, obviously that's a little provocative, but I do think it gets at something true, which is if you reflect on the current state of how deep learning works, it's not necessarily the case that you really think of the learning process that is most important to the behavior of the systems you're observing out there in the world as being gradient descent. Arguably, fairly soon or already, the learning which is dominating what you're actually doing when you interact with these systems is in context learning. Now, yeah, Alexander's got a sad face on. So maybe in context learning has been a bit overhyped, but let me super hype it by saying something about, I think you should take very seriously the idea that it's quite universal for prediction systems with sufficient capability to do as close to Bayesian prediction as they can. If it's possible, right? It's not always possible, it depends on the data distribution. But the data distribution for transformers is very special because it comes in a form that's kind of like closed undertaking prefixes, right? So you see sequences, you see subsequences of sequences, and you're predicting on all of them. And that's arguably, I mean, if you believe the argument that data is what sort of drives to a large degree the behavior of these large learning machines, then this property of the data distribution has to be taken very seriously. So to say that such things are virtual Bayesians is to say that when they're making predictions in the forward pass, and the typical examples that have been studied sort of systematically and in which this has some kind of like rigorous support, including people proving that actually prediction in context is truly Bayesian, is where the input sequences have this sort of, rather than being generic text, have some sort of very specific form that looks like input-output pairs, and then you see an input, and you're asked to predict, this is the input sequence to a transformer, and you're asked to predict the next token, which means to predict something that fits this pattern. And there's a conjecture in this sort of little mini literature that's been evolving over the last few years and has become very popular recently, arguing that actually the way this prediction happens is that in the forward pass, the model is forming something like a predictive distribution and using it to predict. At the moment, the evidence is, kind of interesting on some small examples. Time, yeah. No, go ahead with the question. I think he's just warning me, yeah.
Before you can do Bayesian reasoning from a virtual parameter over a virtual parameter space to a virtual stereo and so on, you need to decide what is that parameter space? Like, is it all of the Turing machines and you're doing solid-enough induction, or is it like linear regression because you consider your hypothesis classes? And so what? That's not part of being Bayesian. That's about something kind of before you decide how to reason. Where does that fit into the story?
Yeah, I don't know. It's a good question. I'm stating a belief I have that this is going to be something very important. It's currently taken seriously by a little sub-literature, but it's a topic on which it's possible that as models become more capable, this becomes more visible. I don't know what these terms mean. That's why it's an open problem. Yeah.
Yeah, as stated, it's sort of kind of vague, also unclear how meaningful it is, because as you say, you can choose a parameter. Okay, but the answer is yes, you can make this precise, and it should be the mixed state presentation of computational mechanics.
No longer an open problem. Good. But one of the things I'd like to highlight is the alignment implications of this potentially, right? It is potentially a big problem for the way we think about interpretability if most of the important construction of structure and execution of algorithms takes place in some virtual setting, right? So that we'd have to actually understand the translation between the base model in some sense and this virtual thing.
Wait, doesn't this just boil down the alignment problem to finding the perfect prompt that you prefix everything with, which is like the best prior?
If you like. Okay, okay. Lambda hat over training, standard phase structure, phase distribution shifts. I'm going to post these slides, SLT for RL. I want to say something about this one because I think this is really cool, and this is something we're actually starting to do. So give me one more minute. As a scientist, I find this proposition extremely depressing or something. I don't know. But whatever, bit of lesson, give up, meat bag, stop doing science, let the model do it, then interpret what the model has done. Maybe not such a bad idea. If you can interpret models, and so Al-Quraishi was the lead author on the OpenFold replication of the AlphaFold paper, and I emailed him at some point asking him, I mean, this is an amazing paper, OpenFold, like very DevInterp-y. It's got phase transitions over training. The transitions have to do with dimensionality of the molecule that's being predicted. It's very cool. And I asked him the following question, which was, okay, you knew about secondary structures in proteins, and you can see that there's phase transitions as the model notices these particular kinds of secondary structures. Is there anything that we could go and like look for phase transitions, and then you would discover something new about proteins? And he was quite excited about the idea of doing that for tertiary structures. Don't ask me to explain what the idea there is. But
what's tertiary structure?
Yeah, I just said don't ask me to explain. Yeah, so this is something we're going to work on potentially. Okay, I'll stop there. Thank you.